Hello, everyone. Thank you for joining. Welcome. My name is Dainis Adamuks. I'm a research engineer in the additive manufacturing team at the MTC, and I'm going to be presenting to you an introductory webinar into additive manufacturing. So before we start, just a few housekeeping points. The session will be recorded and available for you to view later. The mics and videos have been disabled for participants. Also, there are links that are going to be issued with the presentation at the end for you to have a look at some of the other training modules and some more information essentially on the MTC and what we do. So before we start, just a point on the question and answers function. So this should be available to you on your interface. We will be answering questions throughout the presentation, so feel free to ask anything throughout, and we have designated slots essentially available there to answer these. So just a bit of background on the MTC and the high value manufacturing catapults. So we are one of 7 catapults located in Coventry. We are the home of the National Centre for Additive Manufacturing. We are also the ESA AM Benchmarking Centre. And also we are the ASTM AM Centre of Excellence since April 2018. Now, the MTC's main goal is to develop innovative technologies from lower readiness levels, develop them through into manufacturing solutions. So this webinar, just a few points on what we're going to be covering in this introduction. So we're going to be looking at some of the principles of additive manufacturing, the business benefits that additive manufacturing may bring to your companies, looking at process materials and looking at the processes of additive manufacturing and the materials in which these processes can be used to manufacture components. And finally, we're going to be looking at some of the case studies of additive manufacturing and AM adoption. So what is additive manufacturing? Now, manufacturing can be split into 4 main types of process. Subtractive, which is removing material from a solid block to reach a desired shape, such as machining. Formative is using mechanical forces and heat and apply it to material to form it into a desired shape, such as casting, forging. Fabricative, it's using materials combining materials and joining materials together to build components. And finally, additive is the one that we're going to be investigating, which is the process of joining materials, usually driven from 3D model CAD data in a layer by layer fashion. So a question that you might ask is, will additive manufacturing replace conventional manufacturing? Now, the short answer, most probably no. Additive manufacturing is known as a tool within the toolkit of manufacturing companies. So for example, you can see on the left-hand side here, metal injection molding, casting, and forging still dominate the market share for applications where you require a lot greater throughput of components, and also in applications where you need a lot to manufacture a component of a lot greater size and scale. Similarly to in regards to material performance, metal injection molding and forging still dominate areas of the market where you need excellent properties and again very high throughput of components. So when to use additive manufacturing? Some of these questions that are shown on your screen right now are questions that you might ask yourself whether or not you want to adopt AM. So I'm not going to read all of these out, but I'll give a few seconds for you just to have a look at these yourself. Some key questions are, is the performance of a component currently constrained by the manufacturing method? Potentially also, is my supply lead time quite long, and could additive manufacturing be of benefit for me? So we're going to go on to the business benefits of additive manufacturing. The benefits can be drawn down to 3 main areas of point. One is ownership of the supply chain. So using AM, you can drastically reduce the amount of shipping. This is because you can manufacture a component a lot closer to the use case. Again, also because of AM, you can manufacture as and when you require a component. this means that your procurement and physical inventories of these components are drastically reduced because you only need to manufacture when you need this component. Secondly, you can reduce the cost per component using AM. So you can utilize the design freedom to reduce a lot of the excess material from a component, essentially lightweighting the component, which means that you're using both less material, and depending on your use case as well, this might be of better use for you and more cost effective, especially in sort of civil aerospace application. Part consolidation as well. So consolidating a number of subsystem components into one manufactured component reduces the amount of downstream assembly time. So therefore reducing your overall costs per component. And then fast iterations of the design part. So speeding up the prototyping stage during the design and creating functional prototypes drastically reduces the overall cost per component as you're reducing that prototyping effort. You can also improve the component itself and the subsystem that it belongs to. You can increase performance through design freedom, so integrating cooling channels or additional functionality into a component, which otherwise would not be possible through a conventional manufacturing process. Also, customization is something that's really been driven as a benefit with using AM, especially in medical and some consumer products, where that bespoke nature of additive manufacturing really adds benefit to a component. So I'm just going to touch on the rapid prototyping benefit. So you can see through these examples, AM has been used for ergonomic and visual trials. It can be used to manufacture components that can assess the functionality and performance of that component. And they can also be used to support other processes within your manufacturing supply chain. So you can see over here some of the examples of AM being used for rapid prototyping. AM can also be used for tooling and fixturing, and that can have a benefit to your company. So reducing lead times for tools and fixtures that are required is a benefit, because again, it reduces potential manufacturing times, or reduces potential prototyping durations. You can see over here on the right hand side, this tool has also got integrated cooling channels, which improves the service life of this component in industries such as the injection molding industry for both polymer and metal. Another benefit of AM is freedom of geometry. So usually the more complex the geometry is, the less material that is consumed within the manufacturing process. Also, generally, the more complex the geometry is, the more worthwhile additive manufacturing is as a method of manufacture. So these are some of the cases where a lot of material has been removed, driven by topology optimization, but still adheres to the use case requirements. We'd also like to touch on the improvement in component performance. So AM can be used to integrate features and functionality components that otherwise would not be possible using conventional methods. You can see over here the shoulder stem implant on the left-hand side has integrated channeling for direct medicine application without the removal of that implant. You can also see here the thin-walled heat exchanger component is very complex, and through the complexity and added benefit of design freedom, you could actually improve the performance of these components. Again, touching on improving component performance, integrated cooling channels have been used in sort of the tooling industry to increase cycle time, to increase sort of longevity of the part during service. Additional bits can be seen on this slide. Part consolidation is one of the other key benefits of additive manufacturing. Reducing the weight of components by consolidating many components is a benefit. in this case example here, you not only reduce the weight of the component, but also the total height of the component. So this has a knock-on effect on the sub-assembly that that component might belong to. So overall, reducing the potentially the size of your sub-assembly as well. In this case, the clamping unit here is reduced from 3 parts down to 1. So you can see downstream reduction potentially of assembly times using to bolt that component together. And then finally, this is an example where there was quite a large amount of components reduced down into one component, really showing quite a large overall saving in weight. So customization is another key benefit of additive manufacturing. You can see on the left here, interior components, aesthetically pleasing interior components for automotive. Kind of components have been manufactured using additive manufacturing methods, sort of giving a bespoke design to potential sort of users of the technology. With the greater throughput of newer metal technologies such as metal binder jetting, and we've started seeing greater amount of bespoke automotive parts with a large production level of components. So here we can see customizable components from HP and Volkswagen from the automotive sector. And then also medical and dental industries have been utilizing the customization benefit of additive for quite a long time now, and really tailoring components to patients and users for better performance of those components. So we're going to take a small break now and go over some of the questions that I believe we have before we go on to the next section, which is going to be looking into with a bit more detail into the different additive manufacturing processes that there are. So I believe there are some questions there.
Yeah,
Ross?
so Dainis, we've got a couple of questions that have come in on the Q&A. So first one's, what AM standards are the MTC working on?
Right. Okay. So the MTC are working currently. So there is an AM decision guide that's being worked on. So that's going to be a standard on for you to make a decision on which additive process is going to be most suitable for the component. There's also going to be a design for additive manufacturing post-processing. So that's another standard or an activity, a standard activity that is currently ongoing. And then finally, also there is a standard to understand what test artifacts and what testing procedures are required for benchmarking of AM systems. So those are the three that I know that we're currently working on at the MTC.
And there's another one that's come in. So what are the barriers to kind of AM adoption?
The barriers to AM adoption. So I guess high initial capital costs are one. So some of the systems and ancillary systems could be quite expensive, especially for someone looking to adopt at sort of who are at the beginning of that AM adoption journey. I guess lack of understanding of the AM processes themselves and the suitability of those processes to their specific application. So that sort of lack of understanding and knowledge might also be a barrier for them, a barrier standing in the way of them adopting. And then finally, I guess lack of standardization. So touching on the previous question, really. So a lack of standardization across the whole process chain of additive, that potentially could also be a barrier.
Okay, and another one that's come in is, can we print composite materials, and is there kind of an AM method of doing this?
Yes, so in terms of composite materials, the sheet lamination process has a composite variant, which is in its infancy, but it's only been established recently. So I know that there is a process to create composites using sheet lamination. Also material extrusion. So off the top of my head, Mark Forged manufacture a sort of a polymer composite component essentially. So I know there is that process that can manufacture composites as well. And then also, I know that there has been some research into direct energy deposition of metal matrix composites. Again, this is something that's currently in its infancy, but there is potential possibility using DED to manufacture MMCs. So yeah, off the top of my head, though, those are the three that I know of. Again, that's something that we can take offline, and I can speak to some of the more specialized engineers for composites offline, and then we can provide those answers after the webinar. Okay, thank you. I think we're going to carry on for now, Guy, and then we can always refer back to some more of the questions during the other small breaks we have during the presentation. So we're going to look at most of the additive manufacturing processes. So these are the 7 ASTM-driven AM processes. There are other processes out there that either fall sort of between these categories or into a niche category of their own. But we're going to be primarily looking at sort of the more industrially used processes at the moment. So before we start, this is just an AM maturity index from AM Power. So this highlights what AM processes, now these are just the metal ones at the moment, what metal AM processes are the most widespread, what most widespreadly used in industry at the moment, and then also which processes are the most mature. So you can see on the top right hand corner, you've got laser powder bed fusion, the 3DDs, as well as electron beam powder bed fusion. So these are the most prevalent essentially within industry at the moment, and also the most mature. Just below that you have binder jetting and filament FDM, so indirect additive manufacturing processes. There are, according to this, less than 2 years away from industrial use essentially, so definitely pushing into that market. And then you have some other processes like cold spray, I think friction deposition as well. So like friction stir welding, for example, they're really sort of again being pushing into that direction of industrial use. And then you have some more of the other, I guess, less mature, less industrially used processes like nanoparticle jetting. You've got metal SLA in there as well. So just gives you an understanding, a very top level understanding of sort of where we are with industrial uptake and maturity with some of these metal processes. So we're going to touch on sheet lamination. So it's an additive manufacturing process in which sheets of material are bonded to form an object. So during sheet lamination, you have sheets of material, so sheets of a metal. They are machined in this case. Another sheet is then placed on top, and they are ultrasonically welded. The benefit of this process is that you can embed electronics into the different sheets and spaces between those sheets. And that allows you to, of course, manufacture components with embedded sensors, and sort of increases the functionality of your component. You can also weld dissimilar materials and multi-material. You can manufacture components and multi-material capabilities. You can also tailor some of these properties as well as you go through, so which makes them quite beneficial for applications such as heat exchangers. This process isn't really thermal, so those electronics actually survive during the process. However, you do need to machine the component as you go through to get your sort of near-net shape as built component. So we're going to move on to vat photopolymerization. So it's an additive manufacturing process in which liquid photopolymer in a vat is selectively cured by a light activated polymerization. So this is just a top level overview of the 3 different types of vat photopolymerization technologies that are currently out there. Really, in terms of comparison, the SLA system's got probably the best resolution, but it's also the slowest, and it's also not that scalable. So the DLP, it's quicker than the SLA, and it can be scaled up a lot easier than the SLA. However, it's more expensive. It's a more expensive technology. And then finally, the LCD variant of this technology, it's again faster than SLA. It's more easily scaled up due to the fact that you can scale the LCD screens a bit easier and cheaper. And so that's just gives you a very top level overview of the different technologies. So looking at some of the advantages, disadvantages, and use cases for polymer vat photopolymerization, the advantages are that they are fairly low cost systems, and you can manufacture components out with quite good superior detail, resolution, and accuracy. The surface roughness of your components are also going to be quite low due to that low layer thickness. You also have a large range of materials that you can manufacture components out of, and also material vendors, which is also very important. And this range of materials means that there's a range of material properties that are most likely better suited for your application and a better fit. The disadvantages are that the SLA process is quite slow, and you have slow build speeds and slow throughput or low throughput of components. The mechanical properties of these components and materials can sometimes be quite low, and also the components that you manufacture in most cases are towards the lower end in terms of size. Some of the use cases are dental, medical, prototyping, fashion, and then sometimes jigs and fixtures. Also going to touch on ceramic and metal vat photopolymerization. So difference between this technique or this technology for ceramics and metals and polymers is that there are additional indirect additive manufacturing steps such as debind and sinter. So the advantages of this process compared to other metal AM processes is that you get, again, superior detail and resolution, again, due to low layer thickness, and also accuracy and surface roughness of components. Compared to other metal AM systems. The disadvantages are that usually it's quite a high cost process in some cases, again, due to the fact that you have this ancillary equipment, so the furnaces potentially could be of high cost depending on what reducing environments you go for and also what sizes you go for. Again, mirroring sort of what we've seen previously, the low buildability speeds of SLA or vat photopolymerization technologies is a disadvantage. And you tend to find relatively small component sizes, again, and potentially also less material developed for indirect additive manufacturing, with some of the reactive materials being quite difficult to sinter. Uses, high value manufacturing uses potentially, so for high value components such as dental, medical, manufacturing, aerospace, and potentially in petroleum. I'm going to touch on some of the material extrusion technologies now. So it's a process in which material is selectively dispensed through a nozzle or an orifice. So here we can see a polymer and composite version of the material extrusion technology. The advantages are that it's relatively inexpensive compared to other AM processes. It's also quite scalable. Usually you can have a robot or a large gantry driving the head for deposition, which means that you can manufacture a lot large parts. You also have a variety of materials, including some high performance materials. So we mentioned composite previously. You can, yes, some of the systems actually manufacture using a composite material, which significantly improves the strength of these components. Some disadvantages are that usually you tend to find poor surface finish and stair stepping due to the high layer thicknesses used for deposition. Again, it's also a slow building process in some cases compared to other systems, and some of the accuracy could be affected by the moving parts of the system. So the actual way in which the system processes could hinder the accuracy and tolerances of the components. Some of the use cases are, again, prototyping models, jigs, fixtures, tools. Mold cores is an interesting application where you might be able to deposit down the actual mold tool, for example, using this process and then potentially machine it afterwards. And that just saves quite a lot of time and expense from machining out of a different material, essentially, such as metals. And then also for education purposes as well, this process can be used for. Also going to look at material extrusion of metals. So it's an indirect additive manufacturing process in which there is a debind. So there's a print, debind, and sinter step. So the advantage of material extrusion technologies compared to other metal AM technologies is that it's a low-cost system compared to other AM systems. It can also manufacture fairly dense components of 98%, and with some of the newer mature technologies or material extrusion technologies, you will actually print the centering with the component. There will be a ceramic layer deposited within the same system to reduce co-sintering during the sintering stage, which essentially allows you to support significant overhangs, but also remove the support structure quite easily. Some disadvantages are that you tend to find the buildability speeds are quite low, again mirroring previous material extrusion technologies looked at earlier. There is also high build surface roughness and potentially poor interlayer bonding between the layers. Some of the uses, again, high value components within manufacturing, aerospace, and petroleum. Going to look at material jetting now. So material jetting is a process in which droplets of build material are selectively deposited. So during polymer material jetting, as I mentioned previously, droplets of material are deposited onto a substrate. As you can see, those droplets are very small, and therefore one advantage of this technology is that you can manufacture components with high resolution and detail. You also have good component build rates compared to other polymer systems, and your component accuracy is also quite good and quite accurate. You have low surface roughnesses as built. Again, so there's a really minimal amount of sort of surface finishing that you need to do on these components, and also some of the advantages are that you can print in color and use multi-material printing as well, so which essentially just extends or furthers the applications for this technology. Some of the disadvantages are that most of the materials used and components manufactured are of low strength. And potentially also some of the systems, material jetting systems out there could be quite expensive compared to other polymer manufacturing systems or additive manufacturing systems. Some use cases are that you can manufacture smooth, detailed prototypes that convey the final product aesthetics quite well. You can also manufacture accurate molds, jigs, and fixtures and other manufacturing tools, as well as medical models as well. So we're going to look at ceramic and metal material jetting. So this is a system from XJet. It uses, again, just nanoparticle technology in this case. So some of the advantages are that you can manufacture very high resolution and detail metal and ceramic components compared to other metal and ceramic AM systems. There is also a fairly high component build rate for this system over here, and you can manufacture accurate components out of ceramic and metal. Low surface roughnesses as well as built, again reducing the amount of downstream post-processing required. Disadvantages are that the system could be quite expensive. It is an indirect additive manufacturing process. So as you can see in the video, in the next few seconds, there will be sort of like a washing process step and then also a sintering step. So the ancillary equipment required for these steps could be quite expensive depending on which process you go for, or I mean which size of machine you go for in terms of the furnaces. You're also limited to component size in some cases. Again, this is driven by most likely the sintering step. It can become more difficult to sinter larger components. Some of the use cases for these components are manufacturing, high value manufacturing, aerospace, and also the medical industry. So we're going to look at binder jetting. So binder jetting is an additive manufacturing process in which liquid binding agent or bonding agent is selectively deposited to join powder materials. So binder jetting of polymers and sand. So it's a process in which binder is deposited on either polymer or sand feedstock. And then as you're depositing your binder, your build plate moves down, and then a new layer of powder is spread across the top, and then you redeposit the binder strategically as you build up the part. It offers good resolution and detail, also good component build rate, so you can nest many components into there without the need for support structures, which improves the amount of components that you can situate within the build box. There's also fairly good accuracy with components, and you can print in color as well with the polymer systems. And like I mentioned previously, there's no component nest. You can nest your components, sorry, and no support structures required. Some disadvantages are very low strength for some of these components, as they're only very loosely held together. And yeah, some use cases are prototyping with the polymer. However, you can also manufacture casting cores and molds using sand, and that's been quite prevalent within the casting industry. So instead of conventionally manufacturing patterns and molds, you can, which takes up potentially a lot of time and cost, especially on low component number runs. What you can do is you can 3D print using binder jetting of sand, the casting mold or pattern, and then carry on through with your conventional casting process. So you pour to reduce essentially that lead time quite significantly. Also going to touch on metal and ceramic binder jetting. So works very similarly to the polymer system, in which a layer of powder is deposited down, and then binder strategically deposited in a cross section over that powder. You build your component up in that case. It's cured. You remove your powder. You then strategically place your green part onto a ceramic plate or a setter. The part is then debound, so the binder is burnt off, and then it is sintered, where the part will consolidate into your near net shaped final part. So it will shrink with about 20%. The advantages of this process is that you can get high resolution and detail. You're looking at processing sub 25 micron powder with layer thickness about 42 micron. Your build rate is also fairly large, so you have quite a high throughput of components, especially with the larger build envelope systems and the single pass technologies. Utilizing the production variant of manufacture, so manufacturing in batch, improves your throughput of components quite drastically. And again, you can manufacture high accuracy components. These components can be nested, and no support structures required during the actual process. The process itself is also non-thermal, so during sort of the beginning stages here. So once sintered, your properties are more isotropic than what you might find with other sort of metal powder bed processes. The disadvantages are potential development efforts. So you need to sometimes optimize your component or your supporting strategy during these two steps of the sintering. If you don't support to a good enough standard, your component might distort essentially under the active gravity potentially, which severely sort of hinders the component quality essentially. Also, relatively small component sizes can be manufactured using this method, and some of the ancillary equipment, such as the furnaces, could be quite expensive. Use cases, so high value manufacturing parts within a number of sectors. I'm going to take another small break, Guy. So if there are any more questions coming through, I can spend about 5 minutes potentially going through those.
Yeah, brilliant. So we've had a couple. Well, we've had a few more questions. We'll try and get through as many as possible.
Fantastic.
But so there's two from Sai. So let's start with the first one. It says, what is the scope of manufacturing advanced structural ceramics such as silicon nitride within AM?
Good question. I don't know specifically how prevalent the AM of that material is, that's definitely something I can take offline and speak to our sort of specialists in ceramic AM about. I do know that there are a number of new ceramic AM processes. So RoboCast, for example, is one where it's essentially material extrusion of a ceramic, which I believe is robotically driven. But I can't really pinpoint exactly that material and the use case of that material in the current AM landscape. So that's something that I'd like to take offline if possible, Guy.
Yeah, no problem. Well,
Yeah.
we'll try and send out all the kind of the
Yeah,
answers to these
definitely.
questions after anyway. So
Yep.
yeah. The next question we got was some of the procedures mentioned lower mechanical properties. Is it possible to scale the properties? How much less than the conventional techniques? And is the layering technique within AM responsible for lowering these properties?
I'll take this one if you want.
Yeah, sure. From a polymer point of view, go on, Danny.
Yeah, I think that was in relation to most of the polymer ones that pointed out limitations in mechanical properties. You're right that layering, the layering aspect of additive manufacturing does have an impact on this. So your Z strength, as the part is built in Z, often cases will be lower than in the XY plane. This is most certainly the case with material extrusion. But that doesn't mean that you can't achieve good mechanical properties. It's just that for the most common materials, you are a bit more limited. These days, there are actually a lot of high performance polymers available. Material extrusion, you can get Ultem, you can get peaks and PECs and things like that. For VAT photopolymerization, you can get some really high grade materials available for that as well in the past year or so. So I think in the space of a 1 hour webinar, we have to generalize. So the general purpose materials that you find for polymers tend to be quite limited, but that doesn't mean that you can't get some absolutely excellent performance materials.
Okay, and
then
so if we do one more then,
yeah, if you do a few more, I think we're slightly ahead of schedule. So yeah, feel free to.
What is the most important drawback of AM, and is it materials to be processed?
Drawback in a sense of sort of, well, it's quite a general question that I mentioned previously, the barriers to adoption. So some of the drawbacks are high capital costs, not enough real training and understanding the processes and use cases, potentially lack of standardization. Drawbacks also defect modes. So for example, each process usually will have its own range of defects. So there's a lot of optimization work that might be required if a process is needed for your specific application. So potentially, yeah, defects with some of the AM processes. Also, sort of understanding what the quality requirements are in between or in relation to an as-built component using an AM process and a very same geometry as-built component with the same material using a conventional process. What are the different sort of quality developments, or what am I looking at in terms of quality with the two components, if that makes sense?
I think ultimately it comes down to knowledge and understanding, because it is a really broad field of manufacturing now. We have 7 categories here, but within those there are subcategories. So it's industrial's knowledge of the process, how to exploit that technology, when to use it in a business case, that kind of thing.
Yep. So we'll be touching on that slightly with a very top level example of AM adoption in this presentation. And there are also training courses available to sort of go over what that AM journey looks like for people who are interested.
We've got another one as well, maybe about kind of actually IP between different companies. So the question is, how does IP between different tiers of companies in collaboration projects work in platforms such as the MTC or AMRC?
Right. So within the MTC, collaboration projects are usually the funding is taken down from memberships. So if there's 3 tierships of a membership in the MTC: tier 1, tier 2, tier 3. You have different voting rights, and that money that you pay for membership is then drawn down into a project voted on by members. These collaborative projects usually tackle much larger areas of research, and the IP of that research essentially is distributed across the memberships, and that's how it works at the MTC. I'm not sure if that's the same as in the AMRC, but also there are Innovate UK, so government-funded projects. Again, where you have a consortium built up of key technology providers and sort of end users. And again, the IP developed within the research within those types of projects, that IP is distributed sort of equally between all the stakeholders.
Okay, brilliant.
Is that okay? Yep.
Have we got time for one more?
Yeah, go for it.
Okay. So how can metal binder jetting be used for manufacturing like an orthopedic implant from, is it TI6AL4V?
Yeah, so TI64. Okay, so using TI64 material in metal binder jetting or any indirect additive process, as far as I know, is quite difficult, mainly because of potential oxidation of that material. It's very reactive, so it's quite difficult to manufacture using indirect additive AM processes, mainly because we don't, there isn't a reduced environment in the processing itself, or sometimes the debinding. It's not saying that it's not being done. There are systems out there that offer TI64 as a material that you can process with. So I think Digital Metal, I believe Desktop X1, most of them do offer it, but it is quite difficult potentially. In terms of the actual geometry of the orthopedic implant, depends on size. So it depends on size and how complex the geometry is. It might require some optimization for powder removal. So you need to really understand how you're going to remove the powder from this implant, and also centering, so how you're going to support it for centering, and to reduce the amount of warpage, distortion, that kind of thing. But in terms of orthopedics, the high detail that you can get from metal binder jetting and good accuracy really drive or really favor that application potentially, because of the like nice and complex stuff you can do with the latticing, etc. So yeah, potentially it's a good application for it. There are just some optimization and key areas of optimization that might be required. Okay, are we okay to move on there, Guy?
Yeah, I think so.
We can always touch back on some questions at the end of the webinar. So just going to continue on through to metal powder bed fusion, additive manufacturing process in which thermal energy selectively fuses regions of powder bed. So we're going to touch on the first polymer powder bed fusion technique here. So I think the two main techniques. So it's laser. A laser source and a thermal source, as you find with the HP. The main advantages of the thermal source for polymer powder bed is that usually it's a lot quicker than the laser processes. You're sort of more capable of this mid-volume production, higher throughput of components. There's also the full range of color capability. And also no support structure required, which essentially helps downstream when you are processing these components. Some disadvantages are potential limited material variety using this process compared to other polymer processes, and some of these systems actually could be quite expensive. So there is that sort of initial capital cost barrier potentially. The uses, so housings, machinery components, functional testing prototypes, jigs, fixtures, ducting, and potentially other consumer goods, especially if you can manufacture a number of them in a cost-effective manner. So we're going to move on to metal laser powder bed systems. So you can see over here on the left, there's a single laser LPBF system. On the right is a multi-laser LPBF system. So what the advantages of these systems? They're very good at manufacturing high resolution, high detail metal components. These components are fairly accurate as well, and you can achieve considerably large components when comparing them to other metal additive manufacturing processes. So some of the disadvantages, potentially build rate, especially with some of the single laser systems, the throughput you get of components in this technology is a bit lower than potentially other metal AM methods. Some of the systems can also be quite expensive, and all the ancillary equipment, especially with the lasers, could be quite expensive. There was also a requirement to wire EDM the components, so machine them off the base plate, as they will be attached to the base plate. And due to the thermal gradients found as you go up the build of component, you can potentially see some residual stresses, which means that you will most likely need to heat treat the component before wire EDM. Just to touch on also, some of the support structure could be difficult to remove from the components using this method. Use cases, so high value use cases, aerospace components, automotive, medical tooling, some high value components in the different sectors really. Just to touch on the metal laser LPBF hybrid system. So this is a material system which actually includes an integrated machining tool within the metal powder bed. So it has all the advantages of a regular laser powder bed with good resolution, detail, and accuracy. But it's sort of further developed because of this integrated machining tool, which machines around a component every, I believe, five layers, but I'm not too sure about that. It will allow you to have a much better surface, as-built surface finish and as-built accuracy than your sort of conventional LPBF component. But these systems can be quite expensive, and again, you do need to heat treat wire EDM in some cases, and some support structures still present because of the overhangs that you're manufacturing potentially. Good use cases are mold inserts, where you might require a very low surface roughness within the tool that you otherwise couldn't machine post component build. So as you're machining throughout the build, you can actually machine into these very tight and very hard to get to channels and sections. So that's just an advantage there. Electron beam melting, it's another powder bed fusion technique, similar in terms of processing to LPBF, but there is an electron beam gun that melts the powder instead of a laser. With this process, you get fairly good resolution and good accuracy of components, not as superior as laser powder bed fusion, but what you can achieve are good build rates. So this is primarily driven by the size of the powder. You're using a slightly greater powder and slightly greater layer thickness. You also have reduced support material due to the fact that you can nest the components within the build box. So this has two advantages. One is that you don't have to wire EDM the component because the support doesn't actually reach the build plate per se, but also the nesting allows you to have a greater throughput of components per build, which is a benefit. You also have reduced residual stresses. So because the platform is heated, and there isn't that great of a temperature gradient during processing, which means you reduce your residual stresses and you don't really require a heat treatment step. Disadvantages are that it's relatively higher surface roughness, again because of that, because of the size of the powder that you're using. And also it could be quite difficult to remove some of the semi-sintered powder from complex internal features, which might potentially limit the amount, the complexity of components, but also might require optimization in terms of your cleaning strategy. Some use cases: aerospace, automotive, medical, just to name a few. There are other sectors that are available. Again, high value components. So going to look into direct energy deposition now. So it's an AM process which focuses thermal energy to fuse materials by melting them as they are deposited. So one of the most industrially used technologies or members of the DD family of technology is the laser powder processing setup. So with laser powder, you are directing powder feedstock onto a focal point of a laser and using that laser to melt. Four main use cases for this: so you can manufacture a component, so you can build up the component and 2.5, 3-axis, potentially 5-axis if you're using a CNC system, or 6-axis if you're using a robot. But you can build up a component using this type of technology to create an AM component, essentially. You can also repair components. So if you have a component that requires a repair or an additional feature, you can also both repair the component but also include a new feature. So this is very useful and cost effective if you're manufacturing a large component, where you would use a conventional manufacturing method such as casting potentially to manufacture the bulk of the component itself, and then include smaller features around it which you wouldn't really design into your mold or your pattern upstream. Also surface engineering, so coatings. This is a very prevalent technology for coating components for sort of high wear resistant applications. Advantages are that you get good detail, so it's comparatively greater detail compared to other DD systems due to the sort of small layer thicknesses and the feedstock itself. With that also comes greater accuracy of components, and also you can manufacture relatively large components using this system compared to other metal additive manufacturing processes. The disadvantages are that with the blown powder laser, you usually have lower deposition rates than other DED systems. This is not to say that it's still not got a greater throughput of components in terms of buildability than other metal AM systems. It's still actually very high when compared to them. You have slightly reduced component complexity as well in some cases, and this is just due to the DD process. The tool paths that you're manufacturing, with the tool paths that you're using for manufacture, there's quite a lot of optimization. Touching on to this point here, a lot of development effort and optimization required to build complex components, and this is just because there are some trials that need to be done when you want to start working with multiple axes or not just a planar deposition essentially. Potentially YODM, so YODM most likely the bar will have to be machined off the base plate and potentially heat treated before that as well. Again, you've got quite a large gradient of temperature going through there, so it really depends on what your processing procedure is like, and also limited material availability, so some of the reactive materials might not really be best suited for this process. Just touching on some of the hybrid versions of this technology. So I believe HMT offer a laser powder blown processed head that they will bespokely attach or fit to a CNC system that you might have, and essentially that will give you a dual purpose CNC system where you'll be able to build components or add features or build a component, but then machine within the same process flow, and that is quite cost beneficial because it reduces the amount of not only time wasted with or time spent with dataming and repositioning components, but also yeah, it's just more cost effective to include everything into one system instead of buying 2 separate systems, for example. So it's just worthwhile to point out. Arc wire is another widely used combination of thermal sort of heat source and feedstock. Within this technology, usually driven by robot or a gantry, you find a lot superior deposition rates of components. Again, the wire itself, the feedstock that you're depositing, it's a lot greater than the blown powder feedstock, so you're building components a lot quicker. You can also deposit, in some cases, reactive materials, and again, this is purely because it's in the wire form. And again, some of the largest components are achievable with this process. Again, just because of the deposition rates and the actual system itself, it's more driven towards a gantry and a robot system, whereas blown powder is usually situated in a CNC machine system. It's also fairly low cost to implement and to integrate the different bits of kit required for this process. Some of the disadvantages are reduced component complexity, again sort of mirroring what we've seen previously with DD systems. Machining is required due to the high waviness. You can see here the high waviness of the component, so you will have to machine if that's what your component spec is telling you to do. you will also most likely need to wire EDM and heat treat potentially, again due to the thermal gradients, and there is that development factor of some effort required to develop your toolpaths in such a way as you can build more complex components. And again, the use cases, so AM, manufacturing of components, some potentially repair and feature addition as well. I'm going to move on to wire electron beam, DED. So this is a process, again, quite widely used in industry, which uses an electron beam instead of a laser or an arc or TIG or MIG to essentially weld the wire strategically following a toolpath. Again, most of the time driven by gantries and robots. You've got superior deposition rates here, so I believe the electron beam can actually operate at a higher temperature than laser. So you can deposit your weld a lot quicker. You can also deposit reactive and non-weldable materials due to the sort of electron beam heat source. Some of the more larger components are achievable using this process. Main drawbacks and disadvantages are greater cost. You have to conduct everything within a vacuum, so within the cell itself it needs to be vacuumed out, which can incur quite a substantial amount of cost every time you process. But most of the other disadvantages sort of mirror all the other DED systems, where you'll most likely need to wire EDM, development cost, development effort for building complex components, and yeah, reduce complexity in some cases. Use cases, again, so component manufacture, so component repair and feature addition, again mirroring some of the other DED processes. So what I'm going to do is, that sort of wrapped up the main AM processes that we're going to be investigating and looking at the advantages and disadvantages and use cases for. What I'm going to do is sort of highlight an AM implementation case study. So it gives you a bit of an overview of what the sort of the journey to AM adoption looks like and what the steps are. So in this sort of case, we had an industrial company that wanted to investigate 3D printing to manufacture foundry filters. Their main requirements were that the foundry filters needs to be optimized for fluid flow, but also potentially increase the thermal resistance to increase the surface of life of these filters. So actually, they did end up adopting, that was the original surface, the filter, and this was the AM redesigned surface filter. So when you're looking at an implementation case study or an implementation case, there's some questions that you might want to ask yourself, or ask surrounding the requirements. So for example, your component specification is largely going to drive or be driven by what the requirements are for your component, and this can be sort of size, material, the properties you would like to achieve. These are the sort of criteria that really drive what we call the process selection. So just to touch back on a component specification, each requirement that you have will be linked to a certain step within the manufacturing process flow. Now, for example, if my requirement is that I need a certain surface roughness, so a 1.6 or 3.2, that's going to be linked to my post-processing step in my manufacturing process flow. If I know that I need to have an X amount of components measured, or I need to stick to this quality stringency, that's going to affect the inspection manufacturing process within my process flow. So really, it's really about mapping what requirements belong to what process flow. Now, there isn't a hard set of rules to this journey per se. This is a very top level overview of what the questions of what some of the strategies might look like. So then AM process selection, what you want to look at is what are the different AM processes, and which one of these processes might be suitable for my component, and what are the limitations. Some of the redesign stuff, so how can I optimize my component with this chosen process? Are my processes reliable enough for me not to use simulation? Could be a question you might ask yourself. Materials and feedstock, so I understand what material I need from the component requirements, and I understand what processes my material can be used, what materials my process can use, but in what sort of feedstock am I supplying my material in, a wire or a powder, and does it adhere to the specifications and the AM process that I've chosen? Also, post-processing steps. So what are the methods that I need to implement in order to obtain the surface roughness that I might require from a component? It's just a question that you might ask yourself. Inspection quality, how stringent are my inspection and quality needs to achieve the component quality, and what are the inspection limitations? So do you have any line of sight limitations, for example? And then finally, you sort of build up a process flow using all of these different steps, and then you establish a business case. So I will then establish a process workflow that adheres to all the specification criteria, and collate the benefits and limitations of each individual process that I might wish to include, and then factor in the costs of each case. So visually, what that looks like, again, this is a very top level view of some of the journey steps, and this is a strategy that you might want to include when you're distinguishing different business cases for AM processes. That makes sense. So the traditional forming case for this example, at the top over here, I've got the value chain. So there's a process steps. So usually we will start with a model. We will acquire some material. We will do a redesign potentially, or design. We will manufacture the component. We will post-process it, and then we will do some quality control and inspection. So with the traditional forming method, we acquired a ceramic material. There was no design. So actually the negative, so here I've got process benefits and limitations. The benefit was of acquiring the ceramic powder was that was low cost. The limitations were that there was actually no optimization of the component done over here. We formed the ceramic into a foam, which was again is a low cost process. That's a benefit. And the quality check of the component was done to conventional standards, which is a process. It was a benefit because it's less stringent. It's actually less stringent for forming. Now that's cost me £5 a part and a lead time of 1 day. So if I was to implement a ceramic binder jetting technology, I'd acquire the ceramic powder again with the benefit of low cost material, except I have a redesign stage here where I get to optimize my component. So I can actually improve my component performance. So that's a benefit for me. I then 3D print the ceramic filters in batch. Some process limitations because there's potentially higher lead time for that process in comparison to the ceramic forming process. I'll have to sinter my parts because it's a ceramic binder jetting process. So again, it's some additional processing there. And then finally, my quality check is going to be a lot more limited because of the sort of less standards available there for quality inspection. So again, that's a negative. So my component actually costs £150 a piece and take me 3 days lead time in terms of duration, which is greater than what it was originally. But we actually found that the filter itself lasted twice as long as traditionally produced because of this improved performance. And also, not only did it last twice as long, but it actually optimized the flow of metal through the process, the foundry process itself, making it more efficient. So I hope that's just like a very top level understanding of the questions that you could be asking and the assessment you can make when actually implementing or choosing an AM process for you to implement. So that sort of concludes the webinar for today. Now there is some information on training on the AMTC website. Feel free to email myself or my colleague Colin if you want any more information to those training modules. Now, Guy, I believe there are some questions that we can just have enough time to have some answers for.
Yeah. So we've probably got time for a couple. So for the foundry filter case study, is that the data of a particular ceramic, or does it represent a generic ceramic?
I believe this is an alumina ceramic, but I need to double check that.
Mm-hmm.
I don't have that information to hand. I believe it was 99% alumina.
Okay. And we've got so the orthopedic implant manufactured through powder bed fusion. I think the question is, did it require kind of heat treatment to remove residue stresses on the part?
Yeah, for laser powder bed, yeah, it might do. It depends on what how your part is orientated. If there is a great cross-sectional melting, then potentially you might have enough heat built up that you will see residual stresses and therefore need heat treatment. So yeah, most likely if it was LPBF, it will be heat treated. So EBM is more of is a technology that has been used for orthopedics as well. Yep.
Okay. And maybe time for one more then.
Yeah, potentially. How are we doing for time? Yeah, 1 more minute.
1 minute. So how do you take care of distortion in powder bed fusion, and is it good to have a heated build-up plate option? Specifically when you're building small height parts?
Yeah, so there are some systems that offer a greater heated build plate, which significantly reduces the amount of residual stresses. The residual stresses come from thermal gradients in melting, and you can get rid of them through heat treatment mostly.
You can reduce them in build also by support strategies.
Yeah,
so
that's
if
true.
you have more support to the base plate, thicker base plates, that kind of thing, it will hold it in place.
Yep.
And then heat treat after printing to remove those stresses.
That's true. There's also in situ process monitoring as well, which sometimes can pick up areas where there is high sort of thermal activity or high temperature, and you can adapt melting strategies to try and reduce warpage downstream.
Brilliant. All right, thanks for that, Dainis.
Yep.
Just to let everybody know, my colleague Colin has put a link up for all the sort of training courses ran sort of additive manufacturing at the MTC. So if you want to get in touch with him for any information, obviously send him an email on his email that's on the chat. And I'm just going to launch a poll as well. So if you've got a minute and could just literally give us just a couple of pointers as to kind of like how you felt the webinar went. It's really quick. We really appreciate it. So I'm just going to launch that now. Okay, brilliant. Thank you everyone for participating in that, and thank you for also taking part in this webinar. So, hope to see you all soon.
Thanks everyone. Stay safe.
Thank you very much, everyone.